All right, so we are going to discuss bonding today and chemical bonds. And you'll see here why I've chosen this rainbow spectrum for my background. But chemical bonds are very important to understanding all of chemistry. And so let's first start with what is a chemical bond. So that is an attraction that holds two atoms together. And it'll take energy to then pull them apart. So when they're attracted to each other, they like to be there, and it's going to take energy to break any of these chemical bonds. There are two. Oh, why? So then why does this happen? This happens because of the Kardashian effect. Everything wants to be like a noble gas, and they want to achieve full and stable S&P orbitals. They want to have a total of 8 valence electrons, just like the noble gases. And you can achieve this by either losing electrons, metals tend to do this, which makes them positive, or gaining electrons. Nonmetals tend to do this, which makes them negative. So this is when a metal and a nonmetal in an ionic fashion come together. There's going to be a big difference in how much they want those electrons. So one will lose and one will gain. And the other one, so that's ionic. And then covalent is what we say in quote share. It's really more of a battle that never ends. The tug of war never stops because no one loses and no one gains. There's just a anyway. But vernacular, we say share with other elements. All right, so let's explore that. We first of all know the number of valence electrons, hopefully by now. 8 is the maximum because valence electrons only include the S and the P subshells. So anything in the noble gases has 8 valence electrons, even though it's group 18. The one exception is here, helium. Helium should be over here with 2 valence electrons. Anyway, so everything's trying to get 8 except for hydrogen. It's trying to become like helium, which has 2. This has to do, again, with the Kardashian effect. Everything on the periodic table wants to do that. So all of these have 3 valence electrons. All these have 4. Group 14, group 15 have 5. Group 16 have 6. Group 17 have 7. All right. So valence electrons, either the outermost electrons, sort of the vanguard, the first ones you run into, the front lines, as it were, when two atoms come together. They're always just going to be in the S&P, and they thus have a maximum of 8. Remember that the D subshell is filling in the shell below the outermost, and the F subshell is filling in 2 below the outermost. So when you're filling up 4s is when you start filling up 3d, and after you filled up 5s is when you fill up 4d, and when you filled up 6s before you get into the F or the D. So you're always putting these D and F electrons underneath the outermost electrons because the S are always the first ones to go in. All right, so we discussed Boo Boo Jeffries and Scorponok and how Boo Boo Jeffries does not like to fight and Scorponok loves to fight. He's a really good fighter. So that is measured on the periodic table by electronegativity. Boo Boo Jeffries is down in this corner here with the metals, and Scorponok is up here with the halogens and non-metals of that. So these are sort of the ratings you would have if you threw an electron between these two atoms, how well they would fight. So up here, you can see the big numbers. These are the best fighters. And down here are the low numbers. And then it sort of slides as you go that way. So bonding has everything to do with this. Who's fighting over this electron? If one of these high numbers is fighting with one of these low numbers, then that'll be an ionic situation. That's why metals will lose electrons. Here's potassium. It has 1 valence electron. By losing that electron, now it believes it's more like a noble gas. It thinks it's dressed up like a Kardashian. It has the same valence electrons as they do. So losing that electron is not a big loss for potassium. Magnesium, similar situation. It would lose 2 valence electrons. Now it has a stable valence of a noble gas, in this case neon. It thinks it's like neon. It has 10 electrons. It has 8 valence electrons. So magnesium, potassium are examples of atoms that would just lose their electrons, no issues, because, not no issues, but basically no issues, because now they become stable like a noble gas. And who are they losing them to? Well, they're losing them to these nonmetals. Fluorine has 7 valence electrons. It's 1 away from being like a noble gas. By gaining that 1 electron, now it has 8. So it'll take that electron away from a potassium or a sodium or a lithium and now it thinks it has 8 valence electrons and it's noble gassy. Oxygen, same situation, has 6 valence electrons. By taking 2 electrons from something like magnesium, now it thinks it has 8 in its valence electrons. It has 10 total, and so it feels it's stable like a noble gas. So the difference in electronegativity determines whether or not it'll be ionic or covalent. So if there's a large difference, like we were just discussing, that'll be ionic. A small difference, typically when they're both very high, that'll be covalent. So think about it. Ionic bonding is when there's basically a hostile takeover. Here you see this baby took that toy from that baby. There's no question who owns this toy now. He's left with a little nothing, and this kid has all the rings he wants. So atoms lose or gain electrons to become like noble gases. And as we talked about, when sodium loses an electron to chlorine, now sodium thinks it has a noble gas configuration, and chlorine thinks it has a noble gas configuration. And then it's the attraction of that plus ion, because it's one electron down, and minus ion, because it's one electron up, that brings them together. All right, this concept of oxidation reduction is very important in most biological systems. So I'm going to teach it at this point. There's a great way to understand this, and it's Leo Gur. Leo is a lion, this astrological sign for a lion, right? Is Leo, and lions say the word Gur. So Leo should help you understand that losing electrons mean you're oxidized. Gur meaning gaining electrons, you're reduced. Now, why does this happen? Why? And well, before we get into that, real quick, antioxidants, if you've heard of them, the reason they're healthy is because if you have free radicals, which can cause trouble in your body by taking electrons away from healthy atoms, what antioxidants do is provide electrons to those free radicals so they do not attack healthy atoms. So these free radicals are trying to oxidize, lose electrons for other things, right? They're trying to take electrons away. And antioxidants prevents the oxidation of healthy atoms. It prevents them from losing electrons. That's where we get that from. All right. So people always say, why is gaining reduction? That doesn't make sense. Well, think about it. When you gain an electron, you become negative. So your charge is reduced. That's, I think, the logic that went into it. But anyway, everything here in this first row is 1 away from being a noble gas, but it has to go backwards, right? 3 has to go to 2, 11 has to go to 10, 19 has to go to 18. They're all losing an electron. So they lose electrons and become oxidized to be like noble gases, and that's what makes them positive. All of these lose 2 electrons. Beryllium needs to lose 2 to become like helium. Magnesium needs to lose 2 to become like neon. Calcium needs to lose 2 to become like argon, and so forth. So these tend to have a +2 charge. These tend to have a +1 charge. They lose electrons and become oxidized. And the reason for this is, if you think about what the atmosphere is full of oxygen here on Earth, the word came from the fact that oxygen tended to do this to other things. It was the oxygen that was making things lose their electrons because oxygen is such a high electronegativity. All right, on this side of the periodic table, we have things that are gaining electrons, right? Fluorine, chlorine, bromine, iodine. These halogens all want to gain 1 electron to become like a noble gas. Oxygen, sulfur, selenium, these become -2 ions because they want to gain 2 electrons to become like a noble gas, right? Oxygen 2 away from neon, but it needs to pick up 2, so it has a -2 charge. Same with sulfur, same with selenium. Nitrogen, phosphorus, arsenic, these things tend to gain 3 electrons because they're 3 away from the noble gases, so they have a -3 charge. We'll get into some extent why silver, zinc, and aluminum are +1, +2, +3 when we talk more about ionic naming. But basically, if you think about zinc real quick, we said that the noble gas configuration is everything argon is plus 4s2, 3d10. So losing this to always, which is what zinc does, gives zinc a full 3 shell because argon has a 3s2, 3p6, and now it has a 3d10 as well, and it's pretty happy with a full 3rd shell. All right, moving on. So those gain electrons and become reduced. Covalent bonding involves quote unquote sharing. So think about a situation where the fight just never ends because it's pretty equal sides. So the bonding pair of electrons is being fought over. Lone pair are the electrons not necessarily involved in this bonding situation. They're electrons that already were pretty set in the custody of one atom or the other. So chlorine here has three lone pair of electrons and then the one bonding pair. Okay, so covalent bonding, if you look at those orbital diagrams, if you have one with an arrow up and one with an arrow down, they come together, and now the electrons are sort of opposite spins, and that's what they're sharing. Same would be true of fluorine. Fluorine has the one unpaired electron, and by sharing those, that's just a quick. Anyway, moving on. A formula unit for a molecule. We will experience this in class, but basically, a molecule is a freestanding, independent assortment of atoms that are bonded together. A formula unit, because there's sort of a magnetic attraction between the pluses and the minuses, it sort of goes on and on forever and ever and doesn't stop. So by losing an electron, sodium becomes positive, and by gaining that electron, chlorine becomes negative, and these positive and negative ions just stick together over and over again in a lattice. So a formula unit is the smallest repeating thing in that lattice, whereas molecules are these independent, uh, freestanding atoms that are bonded together. So there's a definite beginning and end between that and the next one. All right. Let's discard that real quick. So let's get into a little bit of this. So the difference between covalent and ionic. So like charges will repel each other in anything, like magnets. If you try to put two north ends of a magnet together, there's going to be a repulsion. Whereas opposite charges attract, right? It doesn't take much to bring these together. So, and you should play with this. I've posted it. So the things that lose electrons are your metals. The things that gain electrons are your nonmetals. So that is why ionic things happen. And here we're going to see it. When sodium loses its electron, it goes to chlorine, and then chlorine gets a larger radius, sodium gets a smaller radius, and now you have this plus minus charge ions that want to stick together, like we just saw how opposites attract. Now, because of that, not sure what's happening there, but I guess this is going to happen. There we go. Okay, now because of that, now we have multiple sets of pluses and minuses. It's just going to go on and on and on. So the formula unit is the smallest repeating aspect of that. If you see here, right, they're all going to kind of get together. And just because once one formula unit forms and then another one, they're just going to keep sticking over and over again. So there is no distinct beginning and end as there is with a molecule. These things tend to stick into this lattice. And so we call a formula unit the smallest repeating thing that happens over and over again. Covalently, on the other hand, there's this attraction for those electrons that keeps things in place. Right now, I'm trying to pull them apart, and they don't want to because it takes energy to break a bond. I don't know why that won't let me go forward. Okay, so there we go. Basically, what happens is you have the electrons. This is attracted to its own electron, and now it's starting to be attracted to an electron of another atom. And the same is happening for this nucleus. It's attracted to its own electron and the electron of another atom, and they come together, and it's like they're holding hands now. There's a bond that forms. Notice also that these bonding electrons stay in between these atoms on the same side. So this is unique situation for hydrogen, where now hydrogen has this exposed proton on this side of things. Other atoms would tend to have more electrons around to protect this positive nucleus. But anyway, that's what brings them together. You're talking about the same side of the periodic table, nonmetals and nonmetals having the same attraction for the electrons. So therefore they don't let go. And remember, hydrogen is considered a nonmetal. So it does tend to do these covalent bonds. And then the nice thing here is as you get closer, there's a point where the energy benefit reaches its maximum. right? And then to get any closer, now you have repulsion of those nuclei, positive and positive, and so they push back. So there's basically, this is sort of a nice little bond length. Anyway, probably more than you want to know about that. So that is the difference between a molecule and a formula unit. A formula unit repeats over and over and over again because of that magnetic attraction, whereas molecules tend to be these freestanding things that we'll get into what attraction happens there. So the thing about bonding, though, is at what point do you really say you're no longer sharing, right? At what point does custody of an electron really stop happening for one atom or another? And because of this, we have this sort of middle region of the spectrum. There's one end and there's another end, and then there's this middle area called polar covalent. So we're still going to call it covalent. We're still going to say it's sharing, but the custody of the electron definitely resides with one atom over another. So where you have huge differences like a potassium and a fluorine, it's pretty clear potassium's losing that electron to fluorine, fluorine gains that electron, potassium loses it. But what happens if you get fluorine and boron, right? Not as big a difference. Or if you get, say, carbon and I even use carbon and like aluminum, right? Carbon and aluminum is a closer difference in electronegativity than fluorine and potassium. So could we really say that fluorine, potassium, carbon, and aluminum are doing the same thing? No, we don't really say that. So that's why this polar covalent thing happens. So a covalent polar bond is where control of the electrons spends more time with one than the other. Okay, the custody of these electrons, they spend most of their time with one atom. The other atom, they're just spending weekends or holidays. So polar is when atoms pull unevenly on common electrons. Non-polar is when there's an equal tug on both sides. There is no unequal distribution. So nonpolar will tend to happen when a same thing is pulling itself. So oxygen when it bonds with itself, or fluorine when it bonds with itself, because the fight is between two things that are the exact same thing. So no one is going to have an upper hand. Polar covalent bonds tend to happen when there's a bigger difference in electronegativity, but not such a great difference as a metal and a non-metal, where the takeover is more distinct. Lastly is metallic bonding. So if you think about the electronegativity of all metals, they all kind of don't care. So if you throw electrons out there, they all sort of pass them around like they don't care. The electrons are just sort of swimming around. Noble gas configuration is not achieved by this kind of bonding, but it's still a very strong bond. And the thing, if you think about, if you go to one of those swimming pools where they give you a floaty for nothing, sometimes you'll just let it float away because you don't care, like this guy, right? Because you know there's another one coming if need be. All right. And I think that's all I'm going to talk about there. So we'll discuss properties of these things later.